The topic of the video is scattering amplitude in terms of the phase shifts. For the collision between two particles, uh, for the relative coordinate, we can actually write the part of the Schrodinger equation as minus h square by 2 mu into del square psi of r plus v of r into psi of r is equals to E into psi of r, where v of r is the interaction potential between the particle 1 and particle 2, and then this del square is actually the Laplacian operator expressed in terms of the components of the relative vector. And we can see the derivation of this thing in my previous video on either the Green's function method or maybe the partial wave analysis. So if you express the del square operator in terms of the spherical polar coordinates, which we can actually write like this in the square bracket like this, so the equation becomes this. And to solve this differential equation, we can actually make use of the technique of separation of variables, where we can call this psi r, which depends upon r theta phi, as a product of the function r, big R, which depends just only upon the radial r, and then y, which depends upon theta phi. And in course of derivation, we will be actually calling 1 over y into sine theta dou by dou theta of sine theta dou y by dou theta plus 1 over sine square theta dou y by dou phi square as minus L into L plus 1, and we will be seeing that this y will actually turn into spherical harmonics function, which is ylm theta phi. And then for the radial part of the equation, we get this equation, and in which if you actually make a transformation that if you take r into big R as u, then it actually becomes somewhat simplified function, equation like this. And in the intermediate region, where we can actually ignore the potential v as 0, and if we call 2 mu e by h cut square as k square, then the solution for this differential equation can be taken as a linear combination of spherical Bessel functions jl and nl, like this. And we can write this r as al jl plus bl nl. For large value of kr, we can actually write the function r as al into sine kl minus l pi by 2 all divided by kr minus bl into cos kr minus l pi by 2 all divided by kr, where these BLs and ALs are actually selected through a relationship as BL by AL is equals to minus tan delta L, and this is where we call the delta L as a phase shift. And if we substitute this value of BL, which is equals to minus AL into sine delta L divided by cos delta L, and if you make use of the fact that the numerator in the bracket can be actually simply sine kr minus L pi by 2 plus delta L, so we can actually write r function as simply approximately sine kr L pi by 2 plus delta L divided by kr. And for spherical symmetry, m is equals to 0, the ylm theta phi can be written as pl cos theta, the associated legendary polynomial. So our total wave function for the scattered wave can be actually some constant CL and PL cos theta into sine KR minus L pi by 2 plus delta L all divided by KR, and then summation over all values of these L's. And we can call this as equation number I. So since this sine function is actually exponential I minus exponential minus I divided by 2I kind of equation, so we can actually express this the equation I as this equation, which we can call as equation number 1. But for asymptotic limit, the wave function is usually some normalization factor n into exponential I k dot r plus f theta into a power I k r divided by r. So if you this exponential I k dot r is actually kind of a summation of two terms involving PL cos thetas, like this. So the asymptotic wave function should actually be, will turn into equation number 2. So if you compare the equations number 1 and number 2, then we'll be able to write CL is equal to n into 2l plus 1 into I power l into exponential I delta l. And if you plug in this in equation I, the capital I equation, then we can actually see the wave function for the scattered wave is actually expressed this way. And if we actually kind of compare the coefficients of exponential ikr by r on in equation number 1 and 2, then we will see that this from equation number 1 it is this, and then from equation number 2 it is actually summation of these two terms. So if you do a little bit of mathematics, if you substitute for the value of CL, and if you do a little bit of mathematics of sending this term towards this side, we can actually write f as this expression here, and then we can actually pull out exponential I delta L, and we'll see that it's equal to this into sine delta L PL cos theta. And this is the expression for scattering amplitude in terms of phase shifts. That's it in this video, and thanks for watching.